Alright, so after investigating the concept of numerical and graphical approaches to a limit, we're going to now develop a precise definition of the limit. So for example, when we worked in the previous lesson, we had the limit of the function 2x minus 1 as x approaches 2, the limit was 3. Okay, so we say x is approaching 2, but not equal to 2. So consider the open circle at that position. Then the function is approaching 3. Or another way to say that is when x is close to 2 but not equal to 2, then the function is close to 3. Now, when we're going to talk about a definition, I want you to consider a couple of things. How close should x be to 2? How close should our x be to this value so that our f of x, which is our y, differs from our limit by less than 1. So our limit over here was a 3. So we want to know, this is a delta. We want to know in question, what does delta have to be so that we have this kind of condition. And then the next thing, we can be even more precise. So if I look at 2 and I say, how close should x be to 2? So that our y differs from the limit 3 over here by less than 0.5. Okay, so what we're going to be talking about is a delta epsilon, and we're going to establish a precise definition of the limit. So with that idea in mind of the visual, we have our definition. Okay, let a function be defined on an open interval containing a, except possibly at a itself. Let L be the real number, then the statement, the limit of our function as x approaches a equals L, means that for every epsilon greater than 0, there's a delta greater than 0 such that it's going to satisfy these two inequalities. Okay, so let me just make a note on that. This just means right here, this epsilon greater than 0 measures how close I want, the function f of x to L, to the limit. Okay, and then if we try to break this down over here, this delta, this measures how close x is to a. Okay, and basically when I'm looking at these two inequalities, this is just saying when x is not equal to a, because remember we consider the case when it's that open circle case as well, and x is within delta of a. Okay, that's what that inequality means. And this inequality is just f of x is within epsilon of L. Okay, so let's kind of take these ideas, and I'm going to come down here. Let me clear. And look at this on your paper. Okay, so what we have is this image here, and we have our a, and then we have our limit, and this is our function f of x. So our limit, let me just write our definition over here. So our limit of our function f of x as x approaches a is equal to L. So if we just precisely zoned in only on what we talked about in the previous lesson, and we said as x approaches a, okay, as x approaches a from the left and x approaches a from the right, what is the limit? We just said it was L, right? Now what it's saying is if we are able to choose a delta, an x value that's within delta of a, so like this would be delta distance here, so it's a plus delta, and from here to here is a minus delta, so it's a delta distance. So let's say I pick this particular point here. Okay, if I went up to that and then came over, that would be about, let's see if I can draw a straight line. then that puts my f of x within epsilon of L. Okay, so that's what that's saying. Now, what if I could choose, I'm still, x is within delta of A. Let's say I did this delta. Let's say I let this pick this value. Then you can see that if I choose that delta, does that leave my f of x within epsilon of L? Okay, so what we're doing is we're going to start looking at these values of delta, and we'll consider those to see if it guarantees us to be within epsilon of L. All right, let me erase that. Okay, so we just put that in terms of the definition. Let's just go back to our first page and consider the questions that were presented to us, which probably didn't make much sense at the time, but it says, how close should x be to 2? How close should x be to 2 so that your f of x differs from 3 by less than 1? So basically this is saying if your epsilon is 1, what does our delta have to be so that it guarantees it's within 1 of the value 3? Okay, so that it puts us in this region. And what this question is saying, well, how close should x be to 2, same thing as number 1, if the function differs from 3 by less than epsilon? So what we're saying is if our epsilon value, our distance from our L to the next region, let's say we want to make it even smaller and let's be even more precise, then what does delta have to be to guarantee I'm in that region? So it's kind of what we're going to be toggling back and forth with, this idea of this delta epsilon relationship based on the inequality. So in this part, our epsilon was just 1 here. So the distance from limit L, which we said was 3, was 1. And we said, okay, well, let's make it even smaller. We want our epsilon region to be 0.05 from our limit 3. Then what does that make our delta have to be to guarantee we're in that, that those inequalities are satisfied? Okay, so we're going to come back, keep that idea in mind, but the next thing we're going to do is we're going to practice expressing the limit statement in definition form and also the alternate form, which actually I don't think we even read over that. Let's jump back up to this alternate form. The limit of f of x as x approaches a is equal to L. Just means that for every epsilon greater than 0, there's a delta greater, that should be greater than. There's a delta, I think that's a typo. There's a delta greater than 0, fix that please, such that x is in the open interval from a minus delta, a plus delta. We can see that here. This alternate definition is really visual. And f of x is in the open interval limit minus epsilon and limit plus epsilon. So it's just two different formats to see. Please correct that delta should be greater than 0. All right, so let's now just convert over. I give you a limit, and it's in that form. We're used to seeing it limit of f of x. It doesn't matter. B of t is still a function. As t approaches c, the limit L is k. So if you will, I'm going to let you take a few minutes. Try to rewrite a in definition 2.4 with the new variables and also the alternate definition in 2.5 for this particular example. Okay, so if we change our f of x to v sub t, our x approaches a to t approaches c, and our limit is k, it just means that for every epsilon greater than 0, there's a delta greater than 0 such that this inequality holds, and this just means t is within delta of c. Then we know that our function is within epsilon of our limit k. Okay, this matches 2.4's definition. The alternate definition is just for every epsilon greater than 0, there's a delta greater than 0, such that if t is in the open interval of c minus delta, comma c plus delta, and not equal to c, then the function is guaranteed to be in the open interval k minus epsilon, k plus epsilon. Okay, so here I carried that statement down and I started changing out only part A so far. So we changed it from a left-hand limit only. We changed our function to g of x, and our limit is now c. It means that for every epsilon greater than 0, there's a delta greater than 0, such that, I want to bring attention to this, we only consider the p minus delta part, and if, I know this is going to take the paper with me, but if we come up, what's the left-hand side considered, right? It's just this particular side, so that's why we didn't have to consider the other side as well, so we did the left-hand side. What would it be if I had a right-hand limit? P, yeah, we would have it on the other side, and it would be between P and P plus delta. Okay, good. And then this part stayed the same. Our function changed to g of x. Our limit was c, and it's that stays. So let's together go ahead and change out this particular one to match this left-hand limit for alternate form. So I'm going to erase that and change it now. Okay, so we made the necessary changes to change our function to g of x, and we considered only the left-hand limit, so we're going to be doing the p minus delta to p, and then that's going to change our open interval using our new limit to be that. So one of the things you'll have to practice is formally writing the definition when they give you a new function, a new limit, when they give you a new limit. So write the definition with part A, which is definition 2.4, and also the alternate definition 2.5.